Recall the equation of the tangent line to f of x at x equal a. It's a polynomial of the first degree with the coefficients equal to the y value of f at a and the derivative of f at a. In our terminology, this is a Taylor polynomial of degree 1 at x equal a. In many applications, we approximate f of x with the tangent line. And this involves an approximation error, which is the difference of the two y values, the y value of f and the y value of the linear polynomial. Naturally, the approximation error depends on x. Geometrically, this is the gap, the vertical gap between 2 points on the original graph and the graph of the tangent line. Here's an example. Let's take the function square root of x and analyze its linear approximation near x equal 9. In other words, we want to construct the tangent line to square root of x at x equal 9 and to see how far the tangent line from the original graph is. To find the tangent line, we need to compute the coefficients, the y value at 9 and the value of the derivative at 9. The derivative of square root of x is 1 over 2 square root of x. So when we plug in x equal 9, we get 1 over 2 times square root of 9, which is 1 over 6. And the y value of square root at 9 is 3. So the tangent line is y equals 3 plus x minus 9 over 6. Now let's look at the error, which is the difference in y values between the square root curve and the tangent line. Naturally, that error depends on x, and the closer x to 9, the smaller the error. Let's make a numerical experiment. For instance, let's plug in different x values like x equal 9.5, 9.05, 9.005. In other words, every new x value is 10 times closer to 9 than the previous one. And what happens with the error? You see, whenever we make x 10 times closer than the previous x value, the error decreases by the order about 100 times. So it looks like the error is roughly proportional to the square of the difference between x and 9. For now, this is just a hypothesis. It still needs to be confirmed. In order to better understand the linear approximation error, let's appeal to the physical interpretation. Consider the following example. Suppose we have a car which starts with the initial velocity v0 from the position s0. And we need to estimate the position of the car t seconds after the start. Intuitively, over a short period of times, the velocity doesn't change that much. So it remains approximately equal to the initial velocity. So our position will be the initial position plus the initial velocity times t. That's a linear approximation to the true position. How to interpret the approximation error, which is the difference between the true position and the one obtained from the linear approximation? Let's imagine another car which starts from the same initial position as 0 and the constant velocity v0. So the velocity of that second car does not change. It always stays v0. Then the position of the second car will be exactly s0 plus v0t. So the difference between s of t and the linear approximation can be interpreted as the gap between the two cars. One car travels with generally variable velocity, and the position of that first car is s of t. The other car, it travels with constant velocity v0, so its position changes linearly. Now let's focus entirely on the first car, the one that travels with variable speed. In order to understand how much its true position deviates from linear approximation, we need to understand how much the velocity of that car changes over time. So when we produced linear approximation, we assumed that the velocity doesn't change at all. But if we want to understand the error of the linear approximation, we need to better understand how the true velocity changes over time. So we would need extra information about the acceleration of that car. Suppose we are told that the acceleration of that car always stays between 0 and some maximal value. Can we produce an upper and lower bounds for the true position of that car? Let's look at the extreme scenarios. If we didn't accelerate at all, so our acceleration would always remain 0, then the velocity would not change. It would always stay the same as the initial velocity. Then the position of the car will be the initial position plus the constant velocity times t. In another extreme scenario, let's suppose that we accelerate at the maximum all the time. Then our velocity will change. It will be the initial velocity plus the maximal acceleration times t. The true position will be the antiderivative of this velocity. So it will be the initial position plus v0 times t and plus antiderivative of the last term, which is maximal acceleration times 1/2 t square. These were two extreme scenarios. Since the true acceleration is always between these two extreme values, 0 and a max, the true position of the car will be somewhere between these two values that we obtained. One when there is no acceleration, another when there is maximal acceleration. Note that the difference between these two extreme positions is equal just to this quadratic term. The difference between the true position and one of the extreme cases does not exceed this quadratic term. Thus, the difference between the true position and its linear approximation does not exceed 1/2 of the maximal acceleration times t square. Here is an illustration for our previous example. We are analyzing the position versus time. Since all we know is the initial position and the initial velocity, we don't have a formula for the curve s of t. However, we can use a linear approximation where we estimate the position as the initial position plus the initial velocity times time. Our linear function approximates the true position curve. So there is some approximation error involved. In order to estimate that error, we need additional information. For example, if in addition we require that the acceleration throughout the initial period stays between 0 and some constant a max, then, as we discussed in the previous slide, our linear approximation corresponds to the scenario when the acceleration stays 0 all the time. In another extreme scenario, the acceleration is the maximal all the time. In this case, as we showed in the previous slide, the position is given by a quadratic polynomial of time. Then the maximal possible approximation error is the gap between the linear approximation and the extreme case when acceleration is at maximum. So it will be the difference between the y value of the blue curve and the green straight line. And if we subtract one from another, we are left with just the quadratic term, the maximal value of the acceleration times t squared over 2. In the previous slide, we assumed that the acceleration is between 0 and some maximal positive value. Now, more generally, let's assume that the acceleration can be positive or negative, doesn't matter, but the absolute value of the acceleration does not exceed some constant a max. In that case, the two extreme cases is the acceleration is minus a max and the acceleration plus a max. In the second extreme case, just like in the previous example, the equation for the position will be quadratic, and the quadratic term will appear with positive sign. It's shown on the graph by the blue curve. In the other extreme case, when the acceleration stays equal to minus amax all the time, we get also a quadratic equation of position versus time, but the quadratic term appears with negative sign. The true position is anywhere between these two extreme cases. The linear approximation returns a position right in the middle between the two extreme cases. So the maximal possible error is still the difference between the value returned by the extreme case and the linear approximation. So when you subtract one from another, you still get the same quadratic term as in the previous example. Let's summarize our findings in the following theorem. Suppose we approximate some function f of x with a tangent line at the point x equal a. And suppose we want to estimate the error of this approximation at some value x. Suppose additionally we know that the second derivative of our original function on the interval between a and x does not exceed some value m. So we can think about m as the maximum of the absolute value of the second derivative on the interval from a to x. Then the gap between the original function and the tangent line does not exceed m divided by 2 and times x minus a square. Here's another example. Suppose we are given the initial position, the initial velocity, and the initial acceleration, and nothing else. Then how would we estimate the position after some time t? We can use the same method as in the previous example. The acceleration is approximately equal to the initial acceleration value a0. The integral of this, the velocity, would be approximately initial velocity plus the initial acceleration times time. And if you take integral of this, you will get the position. So you will get a quadratic expression. The initial position plus the initial velocity times time plus, so when you take integral of t, you get t squared over 2. So you get the initial acceleration over 2 times t squared. But how to estimate the approximation error? We need extra assumptions. For example, suppose that we are told that the third derivative of the position, in mechanics it's called jerk. So suppose this third derivative always stays between -1 and 1 meter per second cubed. Now recall that the acceleration is the second derivative of the position. So if the third position is between -1 and 1, then the second derivative will be between integral of -1 and integral of 1. So it will be between the initial acceleration -1 times t and initial acceleration plus 1 times t. And for the velocity, we integrate both sides again. Then we integrate again to get the position. So the position is bounded between two cubic expressions. The two cubic expressions differ only in the cubic term. The sum of the first three terms, this quadratic polynomial, it is the same both at the left and at the right. That's the quadratic approximation for our true position s of t. And the cubic terms, they reveal the maximal error of such approximation. To summarize, given the initial position, velocity, and acceleration, we can approximate the true position after time t as a quadratic polynomial. And if in addition we know the extreme values of the third derivative of the position, then the error of our quadratic approximation does not exceed the maximum of the third derivative divided by 3 factorial times t cubed. Here is an illustration to the previous example. So we have quadratic approximation. Its graph is a green curve. If in addition we assume that the magnitude of the third derivative of the position does not exceed some number m for all times, then we can also look at extreme cases. The extreme case when the third derivative of the position function is plus m, and another case when the third derivative is minus m. The two extreme cases differ only in the cubic term, while the low degree terms are the same as for the quadratic approximation. So the quadratic approximation returns the position which is in the middle between the two extreme cases. So the largest possible approximation error is given by the cubic term, which is the maximum of the third derivative times t cubed over 3 factorial. So how does it generalize to approximation with Taylor polynomials of the nth degree? We want to estimate the remainder, which is the difference between the original value of the function f of x and the one returned by the Taylor polynomial of approximation of degree n. Here's an illustration. So this is our original curve, and this is the Taylor approximation. So the difference between the y values of the two curves, that's the remainder. And the estimate for the remainder is similar to the estimate of the approximation error that we had for quadratic approximation. If we assume that the derivative of order n plus 1 of our function f has a magnitude that does not exceed some number m on the entire interval from a to x, then the magnitude of the remainder does not exceed m divided by n plus 1 factorial times n plus first power of the distance between a and x. This is remarkable because if x minus a is small, then x minus a raised to n plus 1 is going to be much smaller than any lower power of x minus a. So when x is very close to a, the error estimate is going to be much smaller than the value returned by the Taylor polynomial itself. Consider the following basic example. Suppose we have a function e to the x, and we consider its Taylor series near 0. So suppose we approximate e to the x with the first 3 terms of this series. In other words, we are doing quadratic approximation. What will be the error of such approximation at x equals 0.5? We are going to use the Taylor inequality. So the gap between the true value of f of x and the quadratic approximation is less or equal than m divided by 3 factorial times the difference between 0.5 and 0 cubed, where m is the maximum of the third derivative of our function on the interval from 0 to 0.5. So let's recall that why the interval is from 0 to 0.5. 0 is because the Taylor series is applied at 0, like we consider the Taylor series near 0. And 0.5, that's the given value of x. Okay, so let's estimate this constant m. First, all the derivatives of the function e to the x are e to the x itself. In particular, the third derivative is still e to the x. This function is increasing, if you remember. So it reaches the maximum at the rightmost endpoint. So in our case, the rightmost endpoint is 0.5. So the largest value of m is e raised to 0.5, which is at most 1.7. So here we don't have to be precise. It's enough to get some estimate from above, even a rough one. Now, once we estimated m, we go back to the right side of our Taylor inequality and plug in 1.7 instead of m. And the right side is approximately 0.04. For these calculations, we always round up rather than round down. All right, so the true value of e raised to 0.5 is our quadratic approximation, plus minus 0.4. So the quadratic approximation is 1.625, and we have plus minus 0.4. Now, the true value of square root of e is 1.6487. So it is indeed within our bounds that we obtained with the Taylor inequality. So one complication with Taylor series is that sometimes Taylor series, the main idea why we use the Taylor series is to approximate a function with polynomials. Unfortunately, even in cases when function has derivatives of every degree, so you can compute any term of the Taylor polynomial. Let's recall that coefficients of Taylor polynomials, they come from the derivative of f. So even if you compute Taylor series, you are not guaranteed that the series converges to the original function. There are two questions here. First is, if the series converges at all, it's quite possible that the series doesn't even converge, except x equal a. But even when it does converge, it might converge to something totally different. Here's an example. Let's consider a function which is 0 when x is 0, and e to minus 1 over x squared if x is not 0. So the graph of that function, the graph is a bit small, so that's how it looks like. So this is roughly the graph. Okay, so if you try to compute derivatives of f at 0, you will discover that all derivatives of this f of x are actually zeros. So the Taylor polynomial, the Taylor series, will have all coefficients equal to 0. So basically, the Taylor series will be a function which is identically 0. So look, we have a function whose graph is clearly not a constant. But at x equals 0, it becomes so horizontal, not only that it's horizontal, not only that the tangent line has slope 0, but the graph follows the x-axis so closely that all derivatives are zeros. And as a result, even if you know all the derivatives, it makes poor prediction for y values of the function anywhere outside of x equals 0. So luckily, those situations occur quite rarely. So in practice, Taylor series usually provides a very good approximation. But the previous example was a warning that we do need to check convergence of the Taylor series. And moreover, we need to check that the series actually converges to the original function. It's almost always the case, but still, it's a good idea to check. So here's an example. Let's look at the function e to the x. We need to, let's recall its Taylor series near x equals 0. So it's just x to the k over k factorial, the series. And our first question, does the series converge for any x other than 0? So the claim is that actually this series not only converges near x equals 0, but it actually converges for any real x, which is quite remarkable. And the way to check it is just our familiar ratio test. So for a fixed x, you make the ratio of the k plus first term over kth term. And if you do cancellation, you have lots of cancellations, right? So this k cancels. So we get this fraction. You have k factorial divided by k plus 1 factorial, which is k factorial divided by k factorial times k plus 1. So k factorial cancels. You have, that's how you get k plus 1 at the bottom. For a fixed x, when k goes to infinity, the fraction goes to 0. And the 0 is less than 1. So the series converges. So no matter what x is, the series converges. That was easy. However, this only states that the series converges. It does not say that the series converges to e to the x. So how do we know that it converges to e to the x? For that, we need a totally different argument. To see how that type of argument works, let's start with an example. Let's try to understand, let's pick up any x value, for instance, x equal 9. So the Taylor series at x equal 9 will produce this series of numbers. And the y value of the original function at x equal 9 is e to the 9. Let's try to verify that the series actually converges to e to the 9. Well, we have to go to the basics. So let's consider partial sums of the Taylor series. Let's denote nth partial sum by Tn. So we need to show that the sequence of numbers T1 of 9, T2 of 9, T3 of 9, and so on, we need to show that it approaches e to the 9. So how would we do that? We need to investigate the gap between e to the 9 and each of these values of the partial sum. So let's recall that we have the Taylor inequality. Let's compute the gap between e to the 9 and n minus first partial sum when x is 9. So by the Taylor inequality, this is less or equal than, the distance between 9 and 0. Why 0? Because our Taylor series, that's the Taylor series applied at x equals 0. You remember that every time when we compute Taylor series, we compute it near some point. So the Taylor series which contains powers of x, that's the Taylor series at x equals 0. Okay, so we have 9 minus 0 to the n term. Then at the bottom we have n factorial. That's all comes from the Taylor inequality, if you remember. We also multiply by the maximum of the nth derivative of our function on the interval from 0 to 9. What is the maximum of the nth derivative of our function? First of all, what is the nth derivative of our function? Since our function is e to the x, its nth derivative is going to be the same e to the x, right? When you take derivative of e to the x, it's just itself. So our constant m is just the maximum of this function e to the x on the interval from 0 to 9. It's actually instructive to do a picture. So this is our function e to the x. So this is 0. This is 9. And so we are talking about the segment of e to the x from x equals 0 to x equals 9. And we are looking for the maximum of that function. So that's m. All right, so the maximum happened to be at the rightmost point. It's not that important like what exactly the maximum is. The important thing is that the maximum exists and that it does not depend on n. Every derivative of our function f has the same maximum, so it doesn't change. All right, so what happens when n goes to infinity? when n goes to infinity, the right side, what is the right side here? So this right side is effectively a constant multiplied by 9 to the n divided by n factorial. Now, the term 9 to the n over n factorial goes to 0. Why does it go to 0? Well, intuitively, n factorial grows much faster than exponential function. Why is that? Like, it's where does it come from? Well, very simple. The reason is because, if you consider the series 9 to the n over n factorial, that series converges. Why does it converge? Well, we showed it at one of the previous slides that the series with if you replace 9 with any x, the series converges. In particular, it converges when x is 9. And if it converges, then the general term goes to 0. Okay, this is a bit twisted argument. It's possible to show that 9 over n factorial goes to 0 directly without using series. We are just reusing what we already proved just to save time. All right, so the bottom line is that the right side of our Taylor inequality goes to 0. And remember that the right side is overestimate of the gap between e to the 9, the partial sum at 9. So the gap also goes to 0 as n goes to infinity. And this shows that our sequence of partial sums indeed approaches e to the 9. All right, so that's pretty much the argument. Let's try another example. So here we have function cosine x. Its Taylor series near 0. Well, you remember it. It's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus so on. And we can write it in the compact form. And now let's try to prove that this series converges to cosine x for every fixed x. So, okay, so what exactly do we need? Our friend is again the Taylor inequality for this sort of tasks. And let's recall that in Taylor inequality, one of the terms that always appears is we want to estimate the maximum of the derivative of the original function. So for this cosine function, this estimate is particularly easy because every derivative of cosine is a sine wave. Like every derivative of, what are derivatives of cosine? The first derivative is minus sine, the second is minus cosine, the third is sine, then cosine again, etc. So all these derivatives, they have y values between minus 1 and 1. Okay, and so the absolute value of every derivative of cosine is less than 1, less or equal than 1. And it doesn't matter what x is, it doesn't matter what the order of the derivative x, derivative of cosine is. It's always less or equal than 1. So when you write the Taylor inequality, which measures the gap between cosine and the nth partial sum, so the maximum of the n plus first derivative of cosine will be less or equal than 1. And the rest of the terms are familiar. So you have, so this Taylor series is near 0. So you have absolute value of x minus 0 raised to 2 times n plus 1 and divided by 2 times n plus 1 factorial. So the rule of thumb is that the Taylor inequality, the term, algebraically, the term looks very much like the n plus first term of the Taylor series. Lots of similarities. So except for for this overestimate for derivative of cosine, the rest of the terms are looks very similar to the n plus first term of the Taylor series. All right, so we get the estimate. Now, for fixed x, the right side goes to 0. Why is that? Well, let's see. So the right side, you have absolute value of x raised to 2n plus 2 divided by 2n plus 2 factorial, right? And all right, so what do we get? Well, if essentially you have so at the bottom you have factorial, at the top you have exponential function, and similar to what we did in the previous slide, the factorial grows faster than exponential function, so this thing goes to 0. If you want more accurate argument, just observe that you can show directly that the Taylor series converges, so the general term must go to 0. Now we showed that the gap between cosine and nth partial sum goes to 0 as n goes to infinity, and that's exactly what we were trying to prove. So the sequence of partial sums indeed approaches cosine x. In practice, how do we estimate the error in Taylor approximation? The easiest case is when the Taylor series happens to be alternating with decreasing terms. We've already encountered a number of such examples. For instance, the Taylor series for sine, for cosine, for logarithm, for arctangent, the binomial series, and so on. Let's recall that for such alternating series, when we truncate a series, the truncation error does not exceed the next term in the series. In case of a more general Taylor series, we can't use this inequality, but we can use Taylor inequality to estimate the truncation error. You see, the two inequalities are actually look on the first glance look quite similar, but you see the numerator in the Taylor inequality is the maximum of the n plus first derivative on the interval from a to x. So computing that maximum often involves additional work. If the series happens to be alternating with decreasing terms, the numerator is easier. It's just a constant term which comes from the n plus first coefficient of the Taylor series. Finally, it's always a good idea to check your analytic and algebraic work by graphing the remainder. So you just graph the difference between the original function and the approximation. Suppose we are approximating cosine with Taylor polynomial of the 4th degree, and we want our approximation to be accurate within 0.005. In other words, the gap between the two approximations, we want it to be less than 0.005. Cosine is a periodic function. The y values are between -1 and 1. On the other hand, for large x, polynomials go to infinity. So there is no way the polynomial would fit cosine on the entire domain. So we need to determine the interval of x values where the gap between the two functions would be within 0.005. First, let's make a rough estimate of where this interval is. Let's look at the difference between cosine x and its approximation, the polynomial t4. This difference is a function of x. We want to find all the x values for which this function is below 0.005. If we sketch the graph, for instance in Desmos, and if we look where that graph is, where the y values are below 0.05, 1 more 0, 0.005. The x values are going to be roughly between minus 1.2 and 1.2, very roughly. So now let's make a more accurate estimate of those values using series techniques. So first observe that cosine x has a Taylor series expansion. This is alternating series. For alternating series, we have a very easy way to estimate approximation errors, if you remember. Although that way requires the terms of the series to decrease. So do the terms of the series decrease? First of all, the terms of the series, like x to the 2n over 2n factorial, they're all positive. Are they actually decreasing? Let's compare the two terms, like x to 2n over 2n factorial and x to 2n plus 2 divided by 2n plus 2 factorial. Is it true that the higher power, the smaller the terms? Well, that's actually easy to tell because the expression at the right is x to the 2n over 2n factorial multiplied by x squared divided by 2n plus 1 times 2n plus 2. So effectively, we are asking ourselves, is x squared over 2n plus 1 times 2n plus 2? We are asking ourselves if this is less than 1. And in fact, since if we assume that we already got a rough idea what x is, in particular, we can be pretty sure that x is between minus 2 and 2. So assuming that x is between minus 2 and 2, we can say yes. So you see the bottom is, so the top is less than 4, and the bottom for whenever n greater than 1, the bottom will definitely be greater than 4, so the entire fraction will be less than 1. Alright, so we established that this alternating series has decreasing terms. Now let's do the approximation. So we have 1 minus x squared over 2 factorial plus x to the 4 over 6 factorial x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus so on. So we approximated with the sum of the first 3 terms plus the remainder. And that remainder, recall alternating series, so the size of that remainder is less or equal than the next term in the series. So less or equal than the absolute value of x to the 6 over 6 factorial. Okay, and we take absolute value of that. We want this to be less than 0.005. Okay, so we have the inequality to solve. So essentially we have that absolute value of x to the 6 over 6 factorial must be less or equal than 0.005. Okay, so this implies that absolute value of x to the 6 is less or equal than, okay, so let's compute that. So we have 6 factorial times 0.005, which is 3.6. So x itself, its absolute value is less or equal than root of degree 6 from 3.6, which is approximately, well, not even approximately, this is less or equal than 1.237. So that's the interval of x values in which our approximation is within the given bound. Here is another problem. We have log of 1 plus x. Let's recall the Taylor series. So this is alternating series, and we want to estimate logarithm of 1.4. So log of 1.4, that's log of 1 plus 0.4. So using this expansion, it will be 0.4 minus 0.4 squared over 2 plus 0.4 cube over 3, etc. Okay. Now, how many terms do we need to take if we want the answer to be within 0.001? So how many terms do we need to get the answer within 0.001? What exactly do we want here? We are asking, so we want to cut our series. So we want to cut it, we need to decide the value of n such that the remainder would be less than 0.001. So we want the remainder to be less than 0.001. Now, the series is alternating. So for alternating series, it's particularly easy to get an estimate for the remainder. First, observe that not only that it's alternating, but the terms are decreasing. So we have alternating series with decreasing terms. Why are they decreasing? Because we are taking powers of 0.4. 0.4 is less than 1. So whenever you take higher and higher powers, you get smaller and smaller numbers. Also, the bottom is also increasing. So the entire fraction is getting smaller and smaller. Right, so in that case, we have a very simple estimate. So absolute value of the remainder will be less or equal than the first term that we drop, which is going to be 0.4 to n plus 1 divided by n plus 1. Right, so we want this to be less or equal than 0.001 if you want to ensure good approximation. Alright, so essentially we are solving this inequality. Now, this inequality is hard to solve directly because n appears both at the bottom of the fraction and also in the power. So we will use a graphic approach. If we graph the function 0.4 to the x over x, we see that its y values become less than 0.001 when x is approximately 5.5. Essentially, so for all x greater than 6, the y values are going to be fine. So we want x to be integer. X would be greater or equal than 6. So n plus 1 is greater or equal than 6. So n is greater or equal than 5. That will be the answer. Another example. Suppose we have the function e to x squared. And you want to approximate it with a Taylor polynomial. And you want to, so how does it look like? The function looks roughly like this. Okay, and you consider interval from 0 to, it's not a parabola, it's actually a function which grows very fast, much faster than parabola. Okay, and we approximate it on the x interval from 0 to 0.1. All right, so we need to do two things. First, we need to find, we need to approximate with 3 terms. And secondly, we need to find the accuracy of such approximation. All right, so let's start with finding T3. You know, normally you can do, while there is a formula for Taylor series, how to compute coefficients, you need to use it judicially because it's very easy to end up with nasty algebra if you are not careful. So there are various ways to avoid that algebra. Let's start with Taylor series for e to the u near x equals 0, near u equals 0. This is a standard a Taylor series which we already familiar. It's 1 plus u plus u square over 2 factorial plus u cube over 3 factorial plus so on. So it's one of those series that everybody knows. We plug in u equal x square and we get e to x square. By the way, I should write approximately here. So e to x square is 1 plus x square squared over 2 factorial plus x square cube over 3 factorial and plus so on. And let's simplify this expression. So we get 1 plus x square plus x to the 4 over 2 factorial plus x to the 6 over 6 factorial plus so on. Just to be clear, we have only even powers. That means that coefficients at odd powers are zeros. So this is actually 1 plus 0x plus x square plus 0x cube plus x to the 4 over 2 factorial plus so on. We are interested in T3. That means that we are interested in all the powers up to x to the 3. So that's our approximation. And we need to find how accurate it is. Now let's estimate the approximation error. First observe that our approximation T3, it contains only two non-zero terms, 1 and x squared. Where did they come from? Let's recall that they came from 1 and u in the Taylor expansion of e to the u. Rather than estimating the error for e to x squared directly, we are going to estimate the error for replacing e to the u by 1 plus u. We have e to the u is approximately 1 plus u. That's a linear approximation. Let's make a picture. Okay, so e to the u exponential function. The horizontal axis is u, and this approximation with 1 plus u, it's basically the tangent line approximation. So essentially we are estimating the gap between the two approximations for an arbitrary u. In our original interval, x was running from 0 to 0.1. That's x values. Now remember that u is x squared. U runs from 0 to 0.01, right? So once again, u equal x squared, and since x is between 0 and 0.1, u, which is x squared, is going to be between 0 and 0.1 squared. So for estimating the gap in this approximation, that's when we are going to use the Taylor inequality. So the gap between the two sides is m divided by 2 factorial times u minus 0 squared. So we are talking about the interval from 0 to u. Okay. Now what is m? So m, that's the maximum of the second derivative of e to the u on the interval from 0 to u. To get a good estimate, to get a useful estimate, we want m to be a constant. That would solve our problems. What is the second derivative of e to the u? That's e to the u itself. So we are talking about the maximum of the exponential function e to the u. Now let's expand our interval. We'll expand it to be from 0 to 0.01. We'll write less or equal because we are expanding intervals, so the maximum might be a bit larger. E to the u is increasing function, so it reaches the maximum at the right endpoint. We estimated m. We can estimate the entire right side of our Taylor inequality. So we get that m over 2 factorial times u square will be less or equal than e to 0.01 over 2 factorial. Since u is less than 0.01, we estimate from above that u square will be less than 0.01 squared. This number is approximately 6 over 100,000, and that's the accuracy of our approximation on the interval from 0 to 0.1. The advantage of the Taylor polynomial approximation is that the Taylor polynomial Tn is the only nth degree polynomial for which the remainder is much smaller than any power of x whenever x is close to 0. More precisely, the limit of the remainder over x to the n is equal to 0. So any other polynomial of degree for any other polynomial of degree n other than Taylor polynomial, this is not true. The size of the remainder will be comparable with will be greater or comparable with x to the n. Okay, the problem with Taylor polynomial approximation is that it's usually valid only for x very close to 0. So when for large x, this approximation is no longer good. So for many practical problems, people use a different approach. They, instead of trying to fit polynomial very close to x equals 0, they're trying to fit it on some large interval by minimizing the average error, basically minimizing the average gap between the two curves. And depending on how people compute that average gap, there are many ways to compute the average. People use different polynomials to achieve that goal, so-called Legendre polynomials, Chebyshev, Bernstein, and so on.